Not the moon today. So, yeah, thanks for being here and thanks for giving me the opportunity to talk today. I'm going to switch gears a little bit and talk about Mercury. For those of you that do know me, this is sort of a continuation, an upgrade of the modeling work that I was doing on the moon. And if you know Tom, you know that he's been sort of hammering this idea of recombinant desorption to the community for the last 10 years or so. And so this is sort of an update and an upgrade to that model and then adapted to Mercury. So before we get into the details of the model, you know, most of the people are probably better experts than I am in this, but in the 90s, they discovered some bright and depolarizing radar features on Mercury. They then isolated these to the permanently shadowed regions, and because now you have these bright features in a cold spot, they sort of thought, okay, this is water, right? And then the final nail in the coffin about this water debate was really the seminal papers that came from the neutron data and the laser altimeter data aboard the Messenger spacecraft. And so here you can see the neutron data in the red, and then the blue line match is what I remember, the water equivalent hydrogen, which is basically just water ice. And you can see that they match quite well. And then the laser altimeter data was overlapping the height differences between the crater rims and the crater floors of the permanently shadowed regions and the non-permanently shadowed regions. And there was a very distinct difference, and so there is this idea that they were filled with volatiles. Okay, so then another question is, how did water get onto the surface of Mercury? And the most common answer is delivery, and there's nothing wrong with that, considering that Mercury gets about 12 tons of material per day, right? However, there was a recent paper that also brought out the fact that delivery alone cannot really explain the total amount of water that's there without it sort of invoking this really large recent delivery. And so what we're postulating is that there's an additional source term, and that is the solar wind-induced formation, and that can really be broken down into the three steps, basically. So you have these implantation forming these hydroxyl defects, diffusion, and then recombinant desorption. So I'm going to talk more about that in detail. Okay, so this idea of hydroxyl defects from solar wind implantation has been around for a while, right, since the late 60s. And consequently, there have been numerous experiments that have done this. This is one that was done by Micah Scheibel, where he irradiated with protons, KV protons into an olivine sample and an amorphous silicon sample. And you can clearly see this increase in a very broad 2.8 micron band feature, which is attributed to these chemically bound hydroxyls. And the point here is that it forms these hydroxyls and it does not form water directly, right? The second part is diffusion, and the diffusion that I'm doing is not as sophisticated as the stuff that OJ and Bill are doing. And just very quickly, right, I'm just using this analytical solution to 1D diffusion equation. I'm considering a penetration depth of 10 nanometers, which is about where a proton would rest. I'm using an activated diffusion constant from some old experimental papers, considering a spherical grain size of about 60 microns, and I'm only choosing the ones on the surface that are available for recombinant desorption. So that's basically the second part. The third part is recombinant desorption. And so the idea there is that you build up these OH dangling sites on the surface, and then you begin to heat up the substrates. Those will inevitably start to vibrate and wiggle around with each other. They'll interact with each other. At some point, they will react, form molecular water, which desorbs the surface, and then simultaneously heal this oxygen bridge defect. This has, again, been seen since the dawn of beginning of TPD experiments over 100 years ago. But here's just a very nice example of these hydroxyls on the silicate. So you have these geminal and these vicinal sites. You heat it up, you remove the hydroxyls, you form water, and you heal that bridge between the two. And up here is just the IR absorption, so you can see the loss of the hydroxyls as a function of temperature. Okay. The other thing I need to do, or need to know at least for this model, is what the surface of Mercury here. For this, I used just a very basic assumption that the surface of Mercury is consisted of 4 oxides. I assumed a uniform coverage of silicon dioxide at 55%. Then I used these ratio maps that Nittler developed and that are available in the planetary database. And so like for here, this represents the location and concentration of magnesium oxide, calcium oxide, and aluminum oxide. And from there, I just use a linear combination of available activation energies for the overall recombinant desorption rate. And that's what this is right here. So these are the activation energies. This is the prefactor. You plug these into the equation here. Just for normal understanding, you really don't need to pay attention to these numbers. What you need to know is that the temperature right here, where this process begins to happen. On a fully covered surface on silicon dioxide, this starts to happen around 600 Kelvin. And the lowest point is actually titanium dioxide and magnesium oxide. And that actually happens pretty low at 250 Kelvin. Why is that relevant? Well, mercury, as you know, is really hot, right? At its closest point, it's about 750 Kelvin. At its furthest point, it's around 550 to 600 Kelvin, right? So this is a process that's going to be happening on the surface of Mercury. The other thing that I need to know is where the protons are hitting. And for that particular thing, I used this map that Bennett produced. I digitized it to make this. And then here is basically what is happening in the model. You can see that there's a high flux of protons hitting the surface and on the day side temperature as well. So this is just an average. And you can see that it's getting up to about 640 Kelvin. Okay. The other thing that happens is that water interacts with the regolith, right? So Tom talked about this earlier in one of his talks. This is just a temperature program desorption curve. So if you have a monolayer of coverage and you heat it up, a lot of the water will come off about 200 Kelvin, and then it'll be pretty much removed by 400 Kelvin. This high temperature part is just surface reabsorption, so it's hopping from different site to site through the porous material. And then you can extract that to get the energy dependence as a function of coverage, and then from there get a site probability distribution. For this particular thing, I did not take into consideration coverage. I just took the peak here, which is about 65 kilojoules per mole. Anything below that sticks, anything above that will be removed. Then there are other avenues that you have. Everyone's been talking about this. So you have photodissociation. You also have what's considered a dissociated adsorption, where a molecule will hit an active site, split, and produce two OH sites. Kinetic energy loss from, genes escape, basically. So anyways, the point is you have all of these processes happening from your mass balance. You generate these differential equations. You then stick the differential equations into your computer and tell me what's going to happen. Okay, so here are some results. This is where, I'm sorry. That is not frozen water. This is where gas phase water is born. The red line designates the day side and the night side terminators. And so you can see that as soon as the regolith or soil begins to warm up, areas where the proton flux is relatively high, you start to form a lot of water, and that slowly bleeds off as the day progresses. This sharp line right here is just an artifact from the digitization that I did of Bennett's proton map. The equator is a little different. You do see a spike here where the protons are still hitting the surface just at a relatively lower rate. And so they're still there. As soon as the day side comes up, it burns off. And then this peak right here is actually through a diffusion process. The diffusion is still feeding those surface hydroxyls. They'll get to the point where it's warm enough, and then they'll burn off in the recombinant desorption, and then slowly decay back down. And then the night side happens where the process basically shuts off because the temperature is so cold. Okay, so now that tells you where the water was born. Now the question is, where does the water end up? So this is true. This is frozen water. This is a surface map without any permanently shadowed regions. And there's nothing really too exciting here. Again, the red lines represent the day side and the night side terminators. So you can see that the water basically just ends up on the night side and in the polar regions without these permanently shadowed regions. The key thing here is if there is no permanently shadowed cold traps, that wherever the water, 2 minutes, okay. Wherever the water came from, you would end up with a pretty hydrogen-rich or a water-rich exosphere. And so here I digitized the permanently shadowed regions, put them into my map, and you can see that water inevitably went up there and be frozen over geological time periods. You can then summate these, and then here's the black points represent the neutron data that you saw on that first slide. The blue is the simulation, and you can see that it matches quite well. except for this area. This area could very well be just because it's hydrogen rich, right? These are still enough to maybe slow down the neutrons. Or there are other avenues of explanation too, considering the atomic mass in these areas too could be slightly different. The point is that the water will accumulate in these permanently shadowed regions, really regardless of what the source is. The other thing that I considered was hydrogen formation. So this is from Michael Scheibel's paper, where he showed that the hydroxyls are not going to just keep forming when you irradiate them. You will inevitably reach an asymptotic limit. So when you reach this limit, all the protons then will just form hydrogen, and that goes into the exosphere. I did a very simple photodissociation model where I considered hydrogen in the exosphere photodissociation to produce ground state hydrogen, this metastable state hydrogen. That metastable state will then decay and release the Lyman alpha photon. And if you do that, you can actually match well the Mariner 10 data of the hydrogen exosphere. This is H, not H2. So in summary, I guess I am done. Okay, so yeah, water is formed via this method. It can constantly refresh these permanently shadowed regions so that it maintains that high albedo, and that you don't necessarily need to have this sort of random high impact delivery of water to explain the albedos on Mercury. So with that, I'll take any questions. Right, Bill.
Hi, Brant.
Hi, Bill.
Interesting paper.
Thanks.
When you compare your water to the neutron
Yes.
spectrometer, my concern is that you're really talking about a superficial process. In fact, probably we were talking about adsorption and implantation into 30 nanometers, whereas that's pretty thin layer where the neutrons are going down maybe a meter. So it may not be a direct comparison.
Yeah, well, okay, so that's fair enough. All I'm saying is that there's a total amount of water that's accumulating there, and it just happens to match with the neutron data.
Okay,
So I'm not saying that it's a definitive proof that this mechanism happens, but I would like to point out that it's an additional source term that probably should be considered and can help explain some of the results.
Got it.
Yeah.
Got it. Good. Yeah, thanks.
Okay.
Thanks. Ariel Deutsch, Brown University. One thing I was curious about is what you predict about the distribution of how water is forming. There are these regions up Mercury that are PSRs, but they don't appear to have water ice signals. So I was curious about, would you expect it to form uniform or?
Yeah, so that's the weird thing. I don't really know why there are these permanently shadowed regions that have a lower albedo. I guess some people kind of think that maybe there's some sort of amorphous carbon on them, or that there's just no water. But from my perspective, those should be filled with water and have a high albedo. So that should be a relatively uniform distribution.
See, that's why I let Ariel go first, because she asked my question. But I have another question, so no fear. And I've completely. Oh, right. Yeah. No. Here it is. Do you get something like a prediction for how much water should be delivered over geological time, or a rate of supply?
So this model would, so I did the calculation. This model, I calculated within 3 billion years I can generate about 10 to the 14 kilograms. From what I've read in the literature, 10 to the 15 kilograms of water ice is about are estimated on the Mercury, and assuming about 4 billion years of surface inactivity. If that's not true, maybe. I know Ariel publishes, is that true, about 10 to the 15 kilograms? Yeah, okay.
So are you saying a fraction of that could be produced by that? What, 10%? What did you?
Right, yeah, so I'm saying that this can help, if the notion that the delivery alone cannot explain the total amount of water ice on Mercury, recombinant desorption kind of help balance that remainder, so, yeah.
All right, I think we'll take 2 quick questions so that everybody has a time to.
Yeah, just real quick, in your plot where you were showing where the gas molecules were formed,
Yeah.
it died off rather quickly. I was wondering why it died off so quickly.
Where did it, in the equator?
No, in the northern region, yeah, the
Yeah, so that,
Polar
okay,
regions
so
more.
that's fair. That's probably just an artifact of that digitization that I did, right? In that process, it ended up with really harsh and sharp lines. In reality, this would probably be more like kind of a paintbrush that sort of dissipated in intensity, yeah.
Okay, I think we have
Well,
to close.
I think I can answer the question, though, of why you got too little, because of the offset dipole, there should be a very much larger area of open field lines in the southern hemisphere, especially. And so I think if you took that into account, you would get a whole lot more source.
Yeah, that's very true. Yeah, there's definitely more work to be done to this model, and the proton implantation was pretty simple, right? I mean, it was just, I considered it to be constant and uniform throughout the entire simulation, and that's not necessarily true, so.
Okay, I think it was good that my co-chair took that extra minute, so she has to manage that in the next